Hello, welcome everyone. Hope you're all doing well. Hope you all had a great weekend. Before we hop into today's topic, just kind of some reminders about where we are at in the semester. Next week is spring break. I'm pretty sure you're all probably aware of that. So we obviously won't be here next week, but I just want to make sure you're aware that when we get back from spring break, that's going to be an exam week for us. So on the Thursday after we get back from break, it's going to be our second exam. It's going to go a lot like the first exam. It's just the topics are different. So the practice quiz that we had with all the problems on past exams, I believe that's already up. I've got a repository. I still need to add last semester's questions to that repository, and it'll be posted within the next day or two. You can get started prepping for that exam now if you'd like to. Prep for it over spring break, study up if you think that's something that you're going to need to do. I also know that, so I will actually be traveling that week. I am presenting at a conference, so I will not be here to do the review session on Monday the 18th, but I do have a sub. I got somebody to fill in for me, so the next time you come to class, next time you come to this room on Monday, March 18th, it'll be an exam to review day. It won't be me up here, though. It'll be some other people to help you study and prep for the exam instead. So just be aware of that. We do still have class. It will still be a review session. We will still have the exam. All that stuff's going to happen. I will just be in Portland on the other side of the country while all that's going on. So it'll be fun. Trying to think if there's anything else I need to make you aware of. Does anybody have any questions about spring break or schedule or exam stuff before we hop into today's topic? Okay, cool. So, I am assuming that you all probably saw the message that one of the head TAs posted on Piazza last week about this week, or maybe you've heard about the topic that we're talking about this week from other students who've taken the course. Recursion certainly is known as one of the trickier things that we discuss in this class. I think maybe Vicky, the head TA who made that post, was I wouldn't have chanted as much doom and gloom perhaps as she did, but she's definitely right that you should take this seriously, and I would go so far, I would actually take that one step farther and say that if you're having trouble with the material this week, the proper solution is not to power through, right? That is actually the wrong solution. The proper solution is make sure you understand the stuff from last week. If you do not understand how methods work, the content that we talked about last week, you're going to have a bad time this week. You're going to have a bad time trying to understand the material this week. I would go so far as to say that if you, were struggling with methods, you still don't feel super comfortable with methods, that what we're going to talk about today may not be super useful for you. You might want to brush up on that material first and then come back and watch the recording again after you're more familiar with methods. It is just absolutely essential that you have a pretty good understanding, mostly of the flow, right? How methods make us jump around from the code and back. That's going to be one very crucial step to understanding today's material. Because recursion is basically all about using methods to do something that we actually kind of already know how to do a little bit. I'm going to explain that in just a moment. But at its most basic level, recursion can be defined very simply. Recursion is, at its most basic definition, a method that calls itself. That's it. That's quite literally it. Now, as you might understand, this is a tricky topic for a reason. There's kind of, more to it than that. It's actually very easy to write a method that calls itself. That's very simple. But to have a method that does it properly, well, that takes a little bit more thought, a little bit more preparation, a little bit more work. So what I would like to do today is show you some recursive examples. And I'm actually going to start off by showing you a non-recursive example with a problem that I'm hoping that you are somewhat familiar with. I'm going to implement factorial. So just as a little refresher, because I know it's probably been a little while since some of you have maybe thought about factorial. 5 factorial, that's how I would say that, is equal to 5 times 4 times 3 times 2 times 1. So 6, 24, 120 is what that would be, right? That's how we compute factorial. I would like to write a method that can do this for me. So I want a method that will allow me to plug in the value of 5 and spit out 5 factorial, or plug in the value of 7 and spit out 7 factorial, or whatever value factorial I wish to compute. I'm going to do this two ways. I'm going to do this one way pretending that we don't know anything about recursion, which currently we kind of don't, and then I'm going to do it the recursive way, and so we can kind of compare and contrast the two. So for starters, let's do it the non-recursive way, or actually I think the more accurate description would be to call it iterative, or that we're using iterations. Iteration is a sign that we're using loops, so either a for loop or a while loop. If I'm using one of those in my code, I say that my code is using iteration. It's iterating. So I'm going to solve factorial two different ways. I'm going to do an iterative version first. And I forgot one of the magic words here, didn't I? Sorry about that. That's kind of review from last time. We've got two magic words. What's this called again? Return type. That's the return type of the method. This is the name of the method, and then this is an input parameter. So this is what we want to compute the factorial of. I'm going to go through this fairly quickly because it's just going to use concepts that we basically already are aware of. I'll set the total equal to 1, and then I'm actually going to use a while loop. While n is greater than 0, total is equal to total times n. How do I get the value out of a method? I use a return statement. So a return statement is the statement that we use to say, this is your answer, which I want total to be my answer. Again, I know I went through this rather quickly. It's not a terribly complicated piece of code, but let's also verify and make sure that it actually works. I want to, what's it called? So this is a method definition. What's the term that we use when I actually want to use a method? It's a method call. Good. Method call. Method that calls itself. All right. So to call this method, we type out the name. We have to put a value in parentheses for n, so I'll just use 5 so that we hopefully get the same answer as we've computed up here. And then this is going to return a value. So if I want to keep that return value, I have to make a variable to store it in. So store the result of this method call into this variable called v. And then I'll just print it out so we can see what it is. Hopefully we get 120 back out. Let's see. Uh-oh. I made a mistake. I accidentally a thing. Anybody see what I forgot? It's an infinite loop. I was almost there. I just skipped a step. You could tell it was an infinite loop because I started the program and nothing happened. Nothing came out. It was stuck in this loop forever. I meant to decrease n by 1 every time through this loop so that it would progress towards 0. Whoops. I made a mistake. It happens. Let's try it again now that I've fixed this mistake. Hopefully. There's my 120. That's what I was looking for. So think about the way that this works, right? The first time through, n is 5, right? 5 times 1 gives me 5. The next time through the loop, n is 4, right? Next time through the loop, n is 3. So we're doing this. Hopefully you can see that we're doing this. 5 times 4 times 3 times 2 times 1, right? This is not recursive, so I want to make that very clear. This is not recursive, but the reason why I did this is because we're about to do this recursively, and I want to make the point that recursion is another way of doing iteration. So recursion and iteration, not always, but a lot of the times, are two different paths to do the same thing. So if I wish to solve this factorial problem, I could choose to use iteration to do that. That's what I've done here. That means I'm using a loop. Or I could choose to solve it recursively. That's what I'm about to do next. But the point I'm trying to make is that I would not usually generally do both, right? They're two different tools to try and allow us to repeat sections of code. Yes?
I'm just wondering what the difference between a public method and a private method is.
we'll get to that. The question was, what's the difference between a public method and a private method? We'll talk about these. These are called access modifiers in Module 7 when we get to objects. It's a good question, though. Not relevant to us right now. Not today. Yep. Good question. All right. Let's make a recursive version of factorial now. Oops. It's going to have the same basic setup, the same basic signature for the method. I changed the name, right, so we can tell it's the recursive one instead of the iterative one. And so the bare minimum for this to be recursive is that it must call itself. So, you know, this is technically a recursive method. I guess it would need to perhaps return something, right? This is technically, what are you mad at me about now? I'm a little confused as to what this error is saying. Is it a misspell? Oh yeah, I did misspell it. Yep, thank you. There we go. So this is technically recursive, however, it's not useful. It is not useful. In fact, this is pretty similar to the infinite while loop that I was just at before. It's going to take the value of n, and n never changes, so it's just going to keep calling this method over and over and over and over and over and over, and nothing's really going to happen, right? So this is a bad example of doing recursion. While it's technically recursive, it's not helping us. Infinite recursion is bad, just like infinite while loops are typically bad. So in order to do recursion properly, we need two things. We need the recursion, right? We obviously need the recursive method call, but we also need something called a base case. And the base case is our determined ending point for our recursive method. It's basically when we know that we're done. When do we know that we need to stop repeating something over and over and over again? That's what our base case is going to be. So the base case that we might consider here is similar to what we used up here. If n is, you know, less than 0, or I think maybe another way of thinking about the base case is that it's a known value. The base case is just simply a known value. So if n is equal to 1, I don't really need to do any computation, right? I know what that answer is. If n is equal to 1, the factorial of 1 is 1. It's a pretty simple case, right? So I can just say that. I can just say, if n is equal to 1, I'm done. That's my answer. My answer is 1. Again, I'm saying that this is something that we're calling the base case. This is when we stop. This is when the recursive method is going to finish doing its work. If n is not 1, that means that we have more work to do. This is where our recursive step is going to come into play. But we can't just call the method and say that we're done. Right? We have to think about, okay, every time I take a trip through this method, what I'm trying to do is replicate one trip through this while loop. Because again, recursion and iteration are two ways of achieving repetition. So one trip through my recursive method is roughly equivalent to one trip through my iterative while loop. So the next time I go through this while loop, what happens? Right, I see there's some multiplication happening, and I see that n is going down by 1. Well, this part is pretty easy to take care of. If I say n minus 1 here, right, then the next time I go through, if n was 5 before, it'll be 1 less than that. It'll be 4, and then 3, and then 2. But we still have to take care of the multiplication. The multiplication says that I have to multiply by n. And this is probably the trickiest part, I would say, of writing any recursive method. It really it really requires an understanding of what we call the recursive substructure of a problem. So when looking at the recursive substructure, or trying to determine the recursive substructure of the problem, what we're really trying to do is define the problem generally. Here I've given a specific case, factorial of 5, and how to compute it. Okay, how would I generalize that? How would I say, you know, the factorial of n? So n factorial is equal to n times n minus 1 times n minus 2 times n minus 3, right? So on and so forth until I get to 1. Correct? Everybody with me? Do you see in here another factorial that exists? I do. The factorial of 5 contains the factorial of 4. There it is, right there. You see it? That's the factorial of 4. The factorial of n, if I try to generalize this, is going to contain the factorial of n minus 1. Do you agree? So another way of writing this out is to say that n factorial is equal to n times n minus 1 factorial. Do you agree with that statement? I hope. This is the magic. I've defined a problem in terms of a smaller version of itself, right? The word smaller is maybe not the most accurate description there, but it's a, you know, there's fewer steps to compute this than there are to this, or I think maybe the more proper way to say that is that this is one step closer to my base case. If I'm subtracting 1, subtracting 1, subtracting 1, I'm eventually going to hit my base case, right? Where n is equal to 1. And that's when I'll stop. So identifying this recursive substructure goes a long way to helping us write the recursive code. We can actually say this in code directly. This is the method that we're writing. So this becomes our method call. I actually already did that part. Recursive of n minus 1. We just need this out in front. So I'll just say that. And we're missing one final step, which is to say that this is our answer. And I'm making the claim now that this method is going to do the exact same thing that this method does. It's going to give me the same computations, the same results, the same answers. It's just doing it in a different way. It's doing it using recursion instead of using iteration, instead of using a loop. I want to show that to you, though. I actually want to prove it to you, right? Because I think that you can very obviously see these two methods look very different from each other. Very, very, very different from each other. We're using the recursive call to replicate this repetition that we normally would get from a loop, a for loop or a while loop. So the next thing I'm going to do is use my, well, let me actually run it for you. If I switch this to use the recursive version, we should get the same answer. The goal is that I still get the same exact answer even though I did it in a slightly different way. So if I run this, hopefully we see 120 pops out. That's great. That's what I was hoping for. But I want to do even better. I actually want to use my favorite tool, the debugger, to step through this code and see how it's actually working, because I think that's going to do, you know, go a lot farther towards helping your understanding of this particular problem. So what I'm going to do, I'm going to set a breakpoint here on line 12. That's where this is the first time I call my recursive method, right? This is the very first time. I'm going to start up in debug mode. And then we're just going to walk through and see what happens. Let me switch back to my variables window over here so we can see. All right, we've just started. We just landed on our recursive method. How do I actually go into this method and see what's happening? What's the button I click? Step into. So we talked about this a little bit last time with methods. Since we're using methods, before we saw methods, we only used step over. But now that we have methods, we can use step into to take us into those methods and see how those methods are operating. So I'm going to click step into. And here is our first method call to the recursive method right here, right? This is main down here on the bottom. That's where we always start. We always start at main. Here's our recursive method right here. And you can see that n is 5. That's what we're trying to compute the factorial of, right? The factorial of 5. So we always start by checking the base case. Are we done yet? Should we stop? Here our base case is set to be n is equal to 1. All right, so if n is clearly not 1, it's 5. That means that we're not stopping yet. We have more work to do. So, okay, I'm going to click step and see that we skipped the base case and we jumped down to this recursive step. So it's going to say that it needs to compute 5 times the factorial of 4. But this is a method call. So this entire statement cannot be resolved until we walk through the process of calling this method, right? I have to resolve the factorial of 4 before I can multiply it by 5 to get my answer. So clicking the step into button again, watch what happens. I see that I have two recursive method calls here on my stack now. The first one for n is equal to 5, and now this next one where we can see that n is equal to 4. And we're going to ask the same question. Do we stop yet? Nope, not yet. We're going to do more recursion. So now it's saying 4 times the factorial of 3. We'll step into that one and see a similar story, right? There's my third copy of the method. There's my third. N is now 3. Still haven't hit the base case. All right. Step into it again. N is now 2. Still haven't hit the base case. All right, step into it, and now finally we've hit the base case. Take a look at how many recursive calls we've got. The same method has been used 1, 2, 3, 4, 5 times, right? Ask yourself, how many times would we have gone through this loop up here? Also 5? Yes?
When you go to the method below this one,
Mm-hmm.
and inside the factorial recursive and this one, is that redefined?
So the question was, does this redefine n? I would ask you to think about it in a slightly different way. See how I have this same method appearing here 5 times? Each of those is independent of each other, does not even know that the other one exists. So this same method you can think of as existing 5 times, each with its own value of n. Does that make sense?
My question is, how does n count down?
How does n what?
How does n count down?
I'm saying here that if n was 5, I now the next time want it to be 4. So when I call the method the next time, n is going to have 1 less than it did this time. That's important. I'm glad you're asking about it. It's important because without this, we would never hit our base case. We would never get to the end. We would never stop. As long as we keep hitting this line, that's like we're spinning, we're iterating forever. We eventually need to get to this point where we say, all right, this is the base case and we're going to stop. And the way that we typically do that is by manipulating the input parameters to the methods that we're calling. Yes?
I mean, those 5 independent calls, because they're suggesting different ends, then those 5 values would define finally this method, and that 5 values has to be like, that needs to be calculated.
Correct.
To generate a product function.
Correct.
That has to be stored somewhere, right?
Yeah, we're not done yet. We're only actually about halfway through. So yeah, that seems like that might seem like a little bit of a surprise. You're absolutely right. We haven't actually seen the number 120 come out anywhere yet, right? We will. Hitting the base case actually technically only means you're about halfway through, because these methods are not done yet. These methods are sitting here waiting for all of the methods above them to finish, right? So once this method is done, I have to go back to this one and see what work is left there. And then once that one's done, I have to go back to this one and see what work is left there. And that's actually exactly what we're about to do next. So we've hit n equals 1. We're at the base case. We have now hit a known value. The factorial of 1 is 1. So I'm going to return 1. Where do I go when I return? How do I know where to go when I return? What's the next line I'm going to execute? Where would I look to find that information? Right here in the call stack. I'm going to return to line 31. of the previous method call. That's what this is for. That's what this call stack is quite literally for. When you say return, it literally means return to where the method was called. We're using recursion. That means the method is calling itself. So we're actually returning to a prior version of the method that we're currently in. That's what recursion is telling us to do. So I'm going to take this 1 and I'm going to pass it up the chain. I'm going to say, all right, factorial of 1 is 1. You can now use that to compute the factorial for n is 2, right? Because the factorial of n is 2 contains the factorial of 1. So here it's going to say, all right, the factorial of 2 is 2 times the factorial of 1. I now know that this is equal to 1, so I can compute this, and the answer should be 2, right? The result of factorial 2 should be 2. And then it's going to take that and pass it up the chain to the next one. So to compute the factorial of n is equal to 3, I first had to compute the factorial for n is equal to 2, and then multiply that by 3. 3 times 2 is going to give me 6. So it's going to take that 6, it's going to pass it up to the prior recursive call that's been sitting here this whole time waiting, right? I'm now at n equal to 4. 6 is the value that got returned from the prior recursive call, times 4 gets me 24. Pass that one up the chain. 24 times 5 gets me 120. We'll pass that up. We're now at the original part, the original method call where we started in the main method, and we can print out our value and see there's 120. So what I just described, you can actually work out ahead of time on paper. In fact, I'm going to ask you to do exactly that on the exam that's coming up in a couple of weeks. So I want to show that to you now, right? I can actually figure out what this is and work through the recursive part without even having to execute any of this code, right? I can just read the code and reason about it. So I would like to do that with you next. What I'm about to show you is something called the substitution method. And it's a way that it's a method that we use to evaluate recursion. It's very similar to what I talked about up here regarding the recursive substructure, right? Except we're just going to do it on a very specific example. So where did I begin? I began here with the factorial of 5. All right? So I'm saying factorial of 5 is equal to 4 times the factorial of 4. I'm sorry, 5 times the factorial of 4. I misspoke. Okay, well then what is the factorial of 4? We have to figure that out. Factorial of 4 is equal to 4 times the factorial of 3. Okay, what's the factorial of 3? Factorial of 3 is equal to 3 times the factorial of 2. Factorial of 2 is going to be equal to 2 times the factorial of 1. And now, just as we saw before, 1 is our base case. So here I can just say the factorial of 1 is 1. It's a known value. We know what that is. That's our base case. But we're not done, right? The base case is only about halfway through. We called all these methods. We have to work our way back up the chain to where we originally started. And this is where the substitution method gets its name from, right? Now that I know what the value of this is, I can substitute it in here. And that allows me to finish this computation and see what this value is. So I can revisit factorial of 2. I can substitute in my value of factorial for 1, which is 1, and that gets me a final value of 2. Well, now I know what the factorial of 2 is, and I can substitute that value in here, right? So now I can use that to help me compute the factorial of 3. I can type, there we go. 3 times 2 is equal to 6. And then hopefully you can see how this substitution just proceeds along up the chain. The factorial of 4 is going to be 4 times 6, which is 24. And then finally, factorial of 5 is going to be equal to 5 times 24, which is equal to 120. So the substitution method says, show all of the method calls, all of the recursive method calls that are required to hit the base case, and then once you hit this known value, start substituting it back in and performing the computations on the way back up. Note that this is exactly the mechanism that we just watched in the debugger. We're quite literally mimicking the way the computer is executing this code. Yes?
Are you able to have more than one base case?
Absolutely, yeah. The question is, are you able to have more than one base case? Yes, absolutely you can. You might see that pop up on a homework assignment, perhaps. Sure. I can say else if something else. Else. This is a pretty typical format, though, right? Your recursive methods are almost always going to be if statements. If statement base case, otherwise recursive step. That's pretty common, but it could be if statement base case, if statement base case, if statement base case, otherwise recursive step, right? That's also acceptable. Yep. The important thing is really the same thing that's important when writing a while loop. We have to make sure it stops. So if I were to make the same mistake, oops, didn't mean to delete that. If I were to make the same mistake that I made before, where I forgot to subtract 1 from n every time, this is now infinite. I hope you can see that n is always going to be 5, n will never be 1, so I'll never hit the base case. And what's going to happen? It's just going to sit here and call this method over and 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 over. How many times? I don't know. We can actually, we could really find out if we wanted to, but instead I'll just run it and show you that this many times. I'm scrolling right now. This many times is how many times it tried before it gave. That's a lot of times. A few hundred. And then you get to one of the more famous errors of all time. Stack overflow error. Stack overflow error. What is this in reference to? It's actually in reference to the call stack, the method call stack. What is it saying? It's saying that when you ran this, it kept calling this method, kept calling this method, kept calling this method so many times. Once it gets up to 200 or 300 methods, I don't remember where the exact cutoff is, Java eventually just says, I can't do anymore. It's too many method calls. Can't do it. And for most recursive problems, that should be plenty of method calls in order to solve what you need. It should not be necessary to go this deep into recursion to find the base case, to find the answer. So they're basically making the assumption that if you call a recursive method 300 times and you still haven't hit the base case, that it's probably written incorrectly. It's probably not a properly written recursive method. That's what this error message represents. It means that you have not hit the base case. You have not properly directed your code in such a way that you're guaranteed to stop. So unlike a while loop, it won't sit there and spin infinitely, which is kind of nice. But definitely something we need to be aware of. Any questions about that before I move on to the next example? All right. So for the next example, I'm going to throw in, we're going to keep doing recursion, of course, because that's our topic for today, but we're going to throw in one of everybody's favorite things, which is arrays. So let's take a look at a recursion example that also uses arrays. This one was not in the online materials. This is one that I made up specifically for today's class. This time, however, I've already provided you, provided us rather with an iterative solution to this. So let's briefly talk about what this code is doing, because what our goal is ultimately going to be is to try and replicate this using recursion, just like we did with the last problem. I'm trying to count all of the odd values that appear in an array. So it's giving me an array as an input, and I'm going to write a loop that goes through and checks every value in that array. If it's an odd value, then I'll count it. And then I'll just tell you at the end how many odd values that I found in the array. So here I gave a very simple array. It's got 3 odd values in it, right? 1, 3, and 5. If I call the method upon this array and then print out how many odd values it found, I would expect it to say 3. Let's just go ahead and do that real quick and make sure that I didn't screw this up. I don't think I did. Let's make sure. Yeah, 3 odd values in the array, right? I wish to solve this problem recursively. So just like last time, I'm going to make another method. I'll tack an R on the end for recursion, just so I know this is the recursive version. It needs to take in an array of values, right, to look at, to see, how many odd values there are. And you may have noticed that there was a good amount of overlap between the way that this worked and the way that this one worked, and that was kind of on purpose, right? I was kind of trying to show you that there are things that you can reference, right, in the code and kind of pick out how the multiplication happens, how n goes down by 1, how we stop at roughly the same place. If you try to start down that road here, you run into a little bit of a problem, which is that, if I say something like int count is equal to 0 with the idea that I'm going to start counting odd variables, this is actually a bad idea. This is actually not a great place to do this. Consider, if this method is recursive, then that means that it's going to get used many times, right? We're using recursive methods to do repetition, which means that count is going to get reset to 0 at the beginning of this method every single time. That's not really what I want. What I want is a way to keep track of the count, after all of the values have been looked at. So resist the urge to do this. I think there might even be a bigger problem, which is that here we're using a loop variable I to keep track of our position in the array. And we have kind of a similar issue here. I can start I at 0, but then, the next time I call this method, how do I make sure that I is 1, and then I is 2, and then I is 3? We currently don't have a way to do that, and the big reason why is because we only have one parameter here called values, and methods have a very restrictive scope. The only thing that they can see are the input parameters, or any variables that are created within the methods. But I very clearly need a way to have methods communicate more information than that. And so we're going to use a common technique that's often used with recursion called a helper method. So as programmers, I know we're kind of keeping the training wheels on for you. A lot of times we say, make a method that does this, make a method that does this. But as programmers, you don't often have somebody telling you to do that. You have somebody telling you, make a program that does this, and then it's you, as the programmer, that gets to decide, I need this method and this method and this method. So I'm trying to get you some confidence to feel like you can add new methods if you need to, because we can, and we should. If it will help us, that is absolutely a thing that we should do, and it will help us here. Helper methods serve a couple of purposes. They keep recursive stuff separate from non-recursive stuff. So if there's variables that need to be initialized to a particular value, right, I would keep those separated from the stuff that needs to be repeated, from the stuff that's going to happen over and over and over again. The other thing that it allows us to do, and perhaps the more important thing, allows us to add additional parameters to pass info. So I'm saying, I wish I had a variable to keep track of count that could be shared, across all of these methods. I wish I had a variable called I that I could use to keep track of my position. Well, we can do that. I'm going to make another method called countOddHelper. And the reason why I want to do this is because it allows me to add another parameter. If I want to keep track of I across all of my recursive method calls, then I can include this parameter here to help me do that. And so what that allows us to do as I start to piece together my base case and recursive step here. Oops. Since we now have this additional parameter I, right, we can use I to help us keep track of our base case, because that's actually a very important part of knowing when to stop. If I is greater than or equal to values.length, how many odd numbers am I going to see? If I give you this array and I say count all of the values starting at this position that are odd, and this is, you know, bigger than my array, I'm going to see 0 odd values because I'm already at the end of the array. I've already passed by the end of the array. There's nothing left for me to count. For the recursive step, that's not where I want that to go. That's where we're going to do this check. But we have to be a little bit careful. I don't have this count variable. Still have to kind of figure out how to deal with that. I would actually say, all right, we found an odd value here. So if I make it inside of this if statement, I know for a fact that I have seen one odd value, correct? One odd value. But I still might have more odd values farther on down the array. So for our recursive call, what we would say is, yes, we still need the array, but I'm going to increase I by 1. That's going to tell us to check the rest of the array for odd values. We're getting pretty close. There's still a couple of loose ends that we need to tie up here. If it doesn't have an odd value in this particular spot, then we can just tell it how many odd values we've seen, which is 0. Oh, wait. I need to be careful. Hold on. Let me think about that for a second. Oh, yeah. I got you. If it's not odd, so if it is odd, we've seen 1. This 1 represents the one odd value that we've seen, plus all of the odd values that are to come later. If the value we look at isn't odd, this represents the fact that we have not seen an odd value, but we're still going to keep checking all of the values that come later. This might look like we have 2 recursive steps, but it's really just 1 because we're only ever going to take one of these 2, depending on whether it's odd or even. I would say actually at this point the recursion is done. However, we actually need to revisit this method now. Because I'm using a helper method, I have 2 methods. So the helper, the one that I'm designating as the helper is recursive. The helper does all the recursion, has extra parameters to help. The non-helper method we're going to set initial values, right? Usually that's what it is, setting initial values. But I think perhaps a little bit more specifically, it's going to call the helper method. It's going to kick off the recursion. This method is not recursive, very much not recursive. It's just going to kick off the recursion. Let me show you how it's going to do that. It's going to say count odd helper, pass in values for the array, And then what do we want our initial value of I to be? We want it to be 0. I know this problem is a bit trickier than the last one, so I'm going to run it through the debugger just like I did the last one. But we can actually, I think before I do that, I want to do the substitution method again and talk about the recursive substructure and stuff. In fact, maybe I should have done that before I wrote out the code, because that actually helps with understanding the code quite a bit. But it's, it's not too late. We can do it now. If I'm trying to count the odd values of an array that contains 1, 2, 3, 4, 5, right? That's going to be equal to me looking at this first value, 1, plus counting the odd values of everything that comes after that. So counting the odd values of 2, 3, 4, and 5. Does everybody see that? Look at the first value, see if it's odd or not. If it is, that's 1. If it's not, that's a 0. So counting the odd values of 2, 3, 4, and 5. Oops, forgot my brackets. In this case, I'm looking at the first value and saying, is it odd? It is not odd. So that's going to give me 0. Plus, counting the odd values of everything that comes afterwards. So that would be an array containing 3, 4, and 5. And if we continue along with this substitution method example, we'll see that counting the odd values of 3, 4, and 5 is going to give us another 1. Counting the odd values for, can't type all of a sudden. There we go. Almost to our base case. So here is the interesting part, right? We get to the part where there's nothing left. Or in our code, I is going to be greater than the size of the array. That tells us that we've hit our base case. So that's going to give us the answer of 0, but we're not done yet. We now have to do our substitution on the way back up. You can see that all of these values that I'm adding are going to get tallied as I work my way back up towards the top. So I can substitute in here 1 plus 0 equals 1. And then counting the odd values for the next one up is going to give me 0 plus 1, and so on and so forth. Until you hit the top. I don't know if I'm going to type all this out because it's going to take a while, but well, I could just copy paste. That would be faster. So I think it is valuable to see the whole thing typed out. Oops. One left, last one. Oops. Here is the complete substitution method for this example that we've been working through. But I'm going to go through it with the debugger again, because I think that is also a very valuable way to examine recursion. So let's come up here to the top and set a breakpoint on line 7 here, where I first call my recursive method and start stepping through this program. Verify that our substitution method works properly. I'll step in. Notice that I end up in the non-recursive method first. So when using a helper method, we always end up in this non-recursive method first, and then it kicks off the recursion. It's also possible that we might need to do more stuff here, right, in this method. This one's pretty short, but it's possible we might have to do more stuff here than just one line. But at the very least, we need to kick off the recursion by calling the helper method. So once we step into our recursive helper method, then we'll start actually getting into the substitution value. We can see that I is equal to 0. It's going to check the first value in the array. Well, first it's going to check the base case. I is not greater than or equal to the array length. So it's going to check to see if the value in the array at that position is odd, and it is. So it's going to return 1 plus this recursive call. So we're going to see our stacks start to... Oh, I hit step over instead of step into. I'm sorry about that. That's why I was a little confused why it went back. Let me try that again. I hit the wrong button. All right, now if I step into, there we go. We see our recursive calls starting to stack up here. Still not at the base case for I is equal to 1. The value at position I is not odd, it's even. So I've seen 0 odd values, but I still have to keep going. All right, there we go. More repetition. That's an odd value. That's an even value. That's an odd value. Oh, we've hit our base case. I is equal to 5. That is greater than or equal to the length of the array that we're working with. So that means the answer is 0. There's no odd values outside of the array, certainly. But we're not done. We have to work our way all the way back to where we started. So that 0 gets passed up. I see that I'm going to add a 1 to it. We're doing this step right here. All right. The 1 gets passed up. Now I'm on this step right here. Gets added to a 0. That gets passed up. That gets passed up. You can see I'm hitting these lines on the way back up to add up all of the 1s and 0s, which is going to give me 3 as the accurate count. And that's what gets printed out. There's my 3. So this is a more complicated example. Be happy to take any questions, go over any parts of it again if anybody has any. I know it's trickier than the first one. You do not always have to use a helper method. So that's one piece of advice I want to give people. When to use helper methods? If you see an array, that's a pretty big clue that you might need to use a helper method. Not always, but a lot of the time, if you're trying to do recursion with arrays, a helper method is probably going to be necessary. There are other situations in which helper methods are necessary, but the general case is if you ever have to do some recursive stuff and some not recursive stuff, or if you need some additional parameters to help with the recursion, then a helper method is necessary. Question?
Why can't we put additional parameters in the recursive function?
Up here, you mean?
Yeah.
So one reason why not is because when I am counting odd values, or even if I wanted to talk about factorial, which I know we didn't use a helper method for, right? But if we did, that means there's an extra parameter out here, maybe int I. And if I'm a programmer and I'm computing factorial, I'm expecting to just say, give me the factorial of 5. I'm not expecting to say, give me the factorial of 5 and supply you an int I. I don't know what that means, right? If I'm saying count all the odd values in this array, I'm expecting to just give you the array and then have you tell me how many odd values are in it. I'm not expecting to say count how many odd values are in this array and to give you an integer for I, right? That's more of a back end. That's more of something that happens behind the scenes to help with the computation.
So that extra parameter we're doing with arrays are usually index that we're trying to count?
It's common, but not always. Any piece of information that you're trying to track across all of the recursive calls is a candidate for a parameter. As another way that you could have done this, right? Well, I'm trying to think of how else you could have done this. Yeah. So another way to solve this problem, I don't mind going off on this little tangent. Some people don't like the way that oops, I'm on factorial. I meant to be on this example. Some people don't like the way that I do this, right? That I count stuff. But what if I use a third parameter for the count? I could do that too. I could write this solution a little bit differently this way. It would change, a lot of stuff about how the substitution method works and everything, but I think that it could potentially make it a little bit more clear what's happening. So I'm arguing that I made a small tweak. I used count as a parameter this time. It is still my answer, right? It's still keeping track of my answer. I'm only adding 1 to it when I see an odd value. When I don't see an odd value, I just pass it along without adding anything to it, right? So if you think about how this is going to work, when it sees the 1, it's going to count up by 1. When it sees a 2, it's going to come down here, but this will still just be unchanged from before. And then when I hit my base case, I know that I'm done. I've seen everything. I'm just going to give you the answer. The answer is 3, and I'm done. This actually does change the substitution method pretty significantly, though, right? This substitution method no longer accurately matches the way that our code works, and that's fine. It's just a different way. It's just an alternative way of solving the same problem, and that's totally okay. I want to finish up, unless there's any more questions that I missed. I have one more example I want to show you today, which is even more different still than either of the other examples I've shown you today. We're going to do some drawing to end the day today. I want to draw graph paper. So graph paper, really I just want to draw a grid on the screen. I want to draw a grid on the screen, and I want to have the ability to specify how big the graph paper is, and et cetera, et cetera. But we're going to use recursion to do this. So if can I get just a blank screen on here? Maybe, yeah, all right. So if I get a blank screen on here, let's think about the recursive pattern. I want to put a grid on here, right? I want to put a grid on here. I'm going to argue that to put a grid on here, I could draw a cross right here in the middle, vertical line, horizontal line, and then I have 4 quadrants that I need to draw grids in, correct? 4 more quadrants that I need to draw grids in. So if I wanted to, I could start with the lower left quadrant, draw a cross in there, and then you'd see that I'd have 4 more smaller versions that I need to draw grids in. So we're just going to keep drawing crosses over and over again, vertical line, horizontal line, and then go to each of the quadrants that are generated, and then draw crosses in those, and then go to the quadrants that are generated there, and draw crosses in those. And if we keep doing that, we'll eventually fill up the entire screen with a grid. Let's take a look at the code and start piecing this together. The method that we're given to draw our graph paper provides the lower left coordinate for the x position and the lower left coordinate for the y position, as well as how big the screen is. So you can see we're starting at 0, 0, that's the bottom left corner, and 1, that's the entire length of the window, right? The entire size of the screen. Okay. We wish to draw one horizontal line that exactly cuts that area in half, and one horizontal line that exactly cuts that area in half. I'm going to use the standard draw dot line method for this purpose. Maybe you haven't seen this one before. Maybe you have experimented with it when you were working in some of the past assignments. But we have to give it 2 xy coordinates. So let's see, if I'm doing the horizontal line, the x coordinate is going to go from 0 to 1. But I don't want to use 0 to 1. I want to use the generic coordinates that I have here. So it's going to be the same x coordinate that we start with to the other side, right? Whatever the size is. So the current position plus the size. And the y coordinates are going to go from whatever y coordinate we started from. I'm sorry, let me think about this for a second. We need to do some math here, I believe, right? Because we have to divide. Oh no. Wait. Yeah, we have to divide the size in half. And and then add that to our y position. Ah. And then for our ending y position, it would actually be the same because it's a horizontal line that I'm drawing, so the y is not going to change. Let me test this. I'm not 100% confident in my math. Maybe you can tell. Where's my line? What did I do wrong? Size divided by 2. Oh, I forgot a semicolon over here. That's probably a good thing to start with, huh? Oh, okay, yes, it worked. Let me double back and explain this, right? It's telling us to draw a graph paper on the entire screen, and so I'm starting with the coordinate 0, 0, which is down here, and a size of 1, which is the length of the side. I'm drawing this horizontal line across. I'm actually about to use these same coordinates to draw a vertical line, which will be similar just with the size over 2 in the x direction instead of the y direction. Okay, let's double check this, make sure I've got my cross. Beautiful. If you're confused about this, I know I went through it a little bit quickly, and I'm honestly not going to spend a lot of time on it because it's more geometry than recursion right now. If you're confused about it, you can come talk to me after class, and I can work through the math with you in a little bit more detail, if that would help you. I want to focus on the recursive part. I'm making the claim that I have not just one, but actually 4 different recursive steps here. This quadrant, this quadrant, this quadrant, and this quadrant. So the recursive problem that I'm trying to solve is going here, drawing a cross in the middle, and then visiting each of those and drawing a cross in the middle of those, and then visiting each of those and drawing a cross in the middle of those. All right, let's go ahead and figure out how we're going to tell it to visit this lower left quadrant. I need to tell it the coordinates for that lower left quadrant, the lower left x coordinate, the lower left y coordinate, and the size that I want it to have. Well, this is probably the easiest one to work with. The lower left x and the lower left y are actually the same, right? I started with 0, 0. I drew this cross. I now wish to visit this quadrant. The lower left coordinate of this quadrant is 0, 0, right? So unchanged. The size, however, is going down. It's actually going to be half as wide as the one that I just did. The lines are going to be half as long, right, as the cross that I just drew. So the size is going to be cut in half. Let's run this now, and I think we'll be interested to see where we're at. Okay. There's some progress. How did it know when to stop? It knew when to stop when the size got to be less than 0.05. We can actually tweak this to say how big we want our graph paper to be, right? Basically, when it gets to be so small that I can't see it anymore, then I'm going to stop. That's what that means. But we still have 3 more quadrants to do, so let's do the upper left quadrant next. How do I figure out the coordinates for the upper left quadrant? Well, let's take a look. I started with this 0, 0 and the size. I now need this coordinate. So the x coordinate is the same. The y coordinate is up by size over 2. And still, I'm shrinking the size of the cross in half, so that's going to remain size over 2 as well. Let's run this and see where we're at. Okay. Getting there. Ah, there, it went up top. So it finished the lower right quadrant first, then it went up to the upper left quadrant. Still have 2 more quadrants to go. We're going to do, I guess, lower right next. So the x coordinate is going to shift, but the y coordinate is not. So I'll just take this size over 2 term and add it onto x and remove this term from my y. That should take care of the lower right coordinate, or the lower right quadrant. Might have to speed this up a little. It's going to take a long time to start filling out this graph paper. But it's also kind of fun to watch. Let me speed this up. There we go. Okay, what's interesting about this is that you can see once it gets into this quadrant, it's doing all but the upper right quadrants of all of the smaller ones too, right? Isn't that pretty cool? I think it's pretty cool. We have one quadrant left to do, which is the upper right quadrant. Both of them are going to need this additional factor for the upper right quadrant. And now, when I run this, we'll see that it's going to fill in all 4. So if we give this a second to finish its job, it should fill the entire screen. So a couple things to notice about this problem that are, especially as it relates to, the problems that we've seen before. This one's different. This one has not just one recursive call, but 4 recursive calls. I can have as many as I want, as many as I need, right? In this case, 4 made sense because I had 4 quadrants. When I saw that, I immediately knew I was going to need 4 recursive calls, one for each direction that it goes in. So with these visual problems especially, that can be a useful tip. See how many open areas you have left to work with. That's how many recursive calls you need. But we actually have a name for this problem. This problem is called a divide and conquer problem. Is that spelled properly? I guess, I don't know. It's not an English class. Divide and conquer because after I finish doing whatever work I'm going to do this time, I'm going to split the problem up and go into 4 different directions, right? I'm going to divide and conquer each of those quadrants individually. This is why recursion is useful. I'm going to be honest with you right now. If somebody said, hey, write me a method to compute factorial, I'm doing it this way. I'm not using recursion. It's a great problem to use to explain recursion because it's simple. People can generally understand it, but most people would not use recursion to actually do this, right? It's good exercise. Same thing for this one, right? If I really had an array and I wanted to travel through and count the odd values that were in it, I'd probably do it this way. Could I use recursion to do it? Yeah, I showed you that. I showed you how it's possible. I don't necessarily know that I would do it that way, but these kinds of problems, divide and conquer problems, is it possible to do something like this using loops? Yeah, probably. But divide and conquer problems lend themselves very, very well to recursion. So while you may not see as many of these kinds of problems in this class, if you go on to take more advanced computer science courses after this one, you absolutely will see these kinds of problems in future courses, and you will be expected to use recursion to solve them. Recursion is the go-to tool for solving these kinds of divide and conquer problems. You can use it for other stuff as well, but you don't have to. Unless somebody's telling you that you have to use a loop or recursion, generally it's up to the programmer to decide what the better fit is. And honestly, I'm going to pick iteration, right? I'm going to pick the loop 99% of the time probably, because even though I understand recursion and appreciate it quite a bit, I also think it's somewhat more complicated than just cranking out a simple for loop. So don't assume that just because we have this recursive tool means that I'm going to start shoving it in all over the place. That's not necessarily true. The loops are still very useful, very simple, very straightforward, great tool for doing repetition. I'm just showing you another way that can be used to perform repetition that has some very, very, very good applications, especially as you get farther down the road. Does anybody have any questions? Any questions at all? I know this is a mind-bending topic. If you feel like you still don't understand it, that's normal. That is totally normal. Please let me know what I can do to help with that. I'd be happy to go over any of these examples again in my office. I have office hours. I'm available most of the rest of the week, unless I'm in class. If you want to go through some homework problems or some practice exam problems, I'd be happy to do that as well. But it's in your hands now. That's all I have for you for today, so we're going to go ahead and wrap it up. And we'll see you in the labs on Wednesday and Thursday to do some more recursion. All right? Thanks, everyone.